Okay, so we left off on Monday. We talked about correlation, the correlation coefficient. And so today we will continue on in our section about describing a relationship. All right, guys. Between two numeric variables. Okay. And with correlation, we were able to say things like the direction and the strength can be quantified by some value, right? So correlation allows us to quantify the direction and strength of a linear relationship. And if there is a linear relationship, let's say we were talking about snakes again, my favorite example. Okay, so we were talking about the length of a snake and the width of and the weight of a snake, right? Length versus weight. All right, you guys, I don't know what's going on back there, but let's be respectful, please. Length versus weight. And let's say there's a linear relationship. Okay, so there's a linear relationship, and maybe we found correlation. We said R, I don't know, is equal to 0.95. Right, so there's a strong positive relationship. The scatter plot has indicated that it is linear. And so we would say something like, in general, we expect longer snakes to weigh more than shorter snakes. Okay, and so today what we're going to learn is linear regression, and we're going to learn to quantify this relationship rather than just saying longer snakes tend to weigh more than shorter snakes, and we were able to quantify the strength by saying the correlation is 0.95, but now we're going to try to actually put a quantity when we say a longer snake weighs more than a shorter snake. We can actually put numbers to that. Okay, and so we've got linear regression, and so instead of just saying we expect longer snakes to weigh more than shorter snakes, we will then be able to say something like, if a snake is 1 inch longer than another snake, okay, we expect the weight to be, I'm just making up a number, 15 grams more than the other snake. Okay. And so now we are actually assigning values. So rather than just having this kind of vague sense of, larger X means larger Y, we can actually say, if X goes up by this amount, we're going to predict, we expect or we predict the Y to increase by this amount, or the Y to change by that amount. Okay? And so that's kind of the idea behind linear regression. We want to be able to quantify that relationship. Okay? And so what we're going to do is we make a mathematical model. Okay? So we'll make a mathematical model to represent the linear relationship. Okay? And what we mean by a mathematical model is that a mathematical model is a simplified representation of what is happening in reality. Okay? So at least in this case, is a simplified representation of what is, happening in reality. So, if we think about what are the things that go into determining the weight of a snake, there's a lot of things going on, right? It might depend on how recently the snake has eaten, how much the snake has eaten recently, genetic factors about the snake, and perhaps environmental factors, and all sorts of different things. And to fully understand everything that goes into it, we'd probably need to have a deep understanding of snake biology and snake anatomy, and unless you're unless you're a snake scientist, you probably don't know all of these things. And so, but what we can do is we can just look at data and say, hey, you know what? There seems to be a strong relationship between the length of a snake and the weight of a snake. Can we create a model? And that's what we're going to do. And so with linear regression, we are just creating straight line models. Okay, so and this is as far as we're going to go in this class for this topic. Okay, so with linear regression, we create straight line models. Okay, so we will model the relationship with a straight line. And so from algebra, you probably learned that the equation of a straight line is y equals mx plus b. In statistics, the equation of our regression line is y hat is equal to a plus b times x. Okay, so this is called y hat, and the hat, this part is the hat. Okay, and the hat means it is something related to y, but it is not y. Okay, so when you put the hat over y, it means this is a value related to y, but is not y. Okay, so we distinguish the difference between this related value from y itself by putting a hat on it. And in this case, the related value is our predicted value for y. Okay, our predicted value for y. You'll see the hat appear later on in the course when we talk about p versus p hat. That will make an appearance. And in this case, we've got the hat over y, and it means our predicted value for y. A will be our intercept. B is the slope. And x is our x variable. And the idea here is you've got some data, and we want to create a relationship, an equation, the equation of a line that models this relationship. Okay, so our data, the blue dots, I don't know if you can tell they're blue, but the dots represent the data. Dots are our data. Okay, and the line represents the model. Okay, and the model says that if I'm given a particular value of x, okay, so let's say I'm given this x value, all right? So here I've got an actual value right here. This is a data point, x comma y. This one right here, this is an actual value.
Excuse me?
Yes.
What is the difference between a linear regression and a line of best fit?
So in our class, they are the same. Okay. In our class, they're the same. So we'll talk about what it means to be best fit and this term linear regression and all that. But so we'll start off here and we'll say that here is an actual value. This is some data point where we've got an x coordinate and a y coordinate, and that's this dot right here. Okay. The model, the line represents the model, and the model says that if I take that x value, okay, and I'm going to just kind of draw a line straight down. Okay, well, it's supposed to go right there. Let me just try to. Okay, so we're saying for this particular x value, according to the line, I would have predicted that the value is right here. Okay. So the model, or basically the regression line, says that for this x value, right? So this is where our data point is. This is the x value that we have. For this x value, this is where I would predict the value to be. For this x value, I predict the value of y to be, right here at this point. Okay. So there's a discrepancy between my prediction and the actual value. Okay, so that discrepancy we call a residual. So I'm going to draw a little. Okay, so the difference between the actual value and what we predicted, this is the residual. Okay, so the residual is equal to the actual value minus the predicted value. Okay. Is that okay? So, when we have a model, we're going to have actual values, and we've got predictions, and we have residuals. So that means every single one of these data points, every single one has a residual associated with it. Okay, let me go to the next slide here, and then just copy this image over. Let me just do a little cleanup here. So every single data point has a residual associated with it. Okay, and so that, you know, all of these ones, this is the difference between the actual value and what the line predicts would be the value for that x location. Okay, so given this x value, this is what we would have predicted it would be. Okay, so every data point has a residual. Okay, now some of the residuals are very small because the dot is very close to where we predicted it to be. So this is, you know, a very small residual right here at that location. And then, you know, other dots are larger. This is a larger residual. Okay, so, you know, some residuals are large and others are small. Okay, and then some are positive and some are negative. Okay, and again, the residual is the actual value minus the predicted value. So if the actual value is greater than the predicted, the residual is positive. If it is smaller than the predicted, it is negative. Okay. Another way we can say this: the residual goes with the symbol e, kind of like a error term, and it's the actual y minus the predicted value y hat. That is the equation for residual here. Okay. And when we talk about linear regression and the best fit line, the best fit line is defined as the line that minimizes the sum of squared residuals. All right, so what do I mean by that? So every single data point has a residual, and you can imagine that we take each of these residuals and we turn it into a square. Okay, so I'm going to square each one. All right, and we're going to sum up the total area of these squares. So we find the squares of all of these residuals, and then we add them up. So some squares are tiny, some squares are bigger. And what we want is we want to find the line that minimizes the sum of all of these squares. Okay, and so there's a little applet that, not applet, there's a web page that kind of demos this concept. It's explained visually, and where is this? Ordinary least squares regression. Okay. So right here we have different data points. These are different data points, and we can see each of these data points has a residual, and it has already squared it. So the residual is the difference between the data point and where the line predicts that would be. And yeah, question?
Yeah, so maybe you're about to explain this, but
okay.
This square is like the actual raising to the power of 2.
Yes, we are just taking.
You're also representing as a geometric square.
Yes, we're representing as a geometric square. Yeah, if you multiply something by itself, raising it to the power of 2, you are effectively calculating a square where one of those sides is that number. Okay, so you can represent it geometrically with a square. Yes, so each dot here has a residual, the difference between the line and its thing, and we've created a square. All right, and so we're representing each of these squared residuals with these boxes, And over here represents kind of the sum of all of these squares. So we can see that this purple one, which has a very small residual, has a very small square associated with it, where this brown dot here has a large residual and has a large square associated. And we can see if I change, this gives me the option to change the intercept here, and I can shift the line and we can see how the residuals change, right? So if I shift the intercept to be way up here, we can see this dot is very far from the line, okay? So now it has a huge residual, and when we square it, it has a huge squared residual, okay? And so we can see, we can, kind of adjust all of these, the intercept there, I can adjust the slope here, and we can see, can I find the combination of slope and intercept that minimizes the total sum of squares? Is it possible? And that's what we're trying to do. We're trying to find the combination of intercept and slope that will minimize the sum of squares residuals. Okay, you can kind of play around with it based on this website. I'll copy this into our class notes here. So this is okay. I'll just put this here, and the important part's really just the web address, isn't it?
Professor?
Yes.
Could you repeat the point about squaring and like the shape? So if 3, for example, on a chart, like if you draw a line that's 3 units long, then you're saying, what were you saying about like the square will have an area of 9? Is that what you're saying?
Yeah. Basically, if the length of this side is a 3, when we square it, this square has an area of 9. Okay, so
the area is always what the square value is.
Yes. Yeah. So just you can just visually think of it as, we've got all these squares that are formed. The way these squares are formed is by taking the difference between each dot and the line, and then we say, okay, this is going to be the edge of the side of the square, and therefore I form a box here, right? And what we're trying to do is we're trying to minimize the total area, right? If we say I've got to draw all of these boxes and then paint it in, but paint is made out of gold, and so we want to minimize the amount of gold paint that I have to use for this ridiculous example. We want to find the line that's going to minimize the size of all of those boxes here, okay? So the best fit line is defined as a line that minimizes the sum of squared residuals, okay? And so you can kind of play around with this. And, nice thing for us is that it turns out for every single data set, the best fit line, the least squares line, so this sum of squares residual, this is also called the least squares line. It turns out that, for any data set with a linear relationship, the least squares line will always have these certain properties. These properties have been derived for us using calculus, and we can just reap the benefits. We don't actually have to learn where these things were derived from. But so the least squares line for any data set. For any data set with 2 numeric variables, we'll have the following slope and intercept. Okay, so the slope, which is represented by b, so again, our least squares line is in the form y hat is equal to a plus b times x, where b is the slope and a is the intercept. The slope b is given by r times sy divided by sx, and the intercept a is equal to y bar minus b times x bar. All right, and so there are basically you just need you need 5 summary statistics, right? So you can imagine the data table has a column of x values and a column of y values. I don't know, 10 and 12 and 13 and 17 and maybe 9 and 11 or something like that, and so on and so forth. You've got a bunch of these values. X bar is just the mean of the x column, and SX is the standard deviation of the x column. Okay, and then you just do the same thing for y. Y bar is the mean of the y column, and SY is the standard deviation of the y column. Okay, and so that covers all of these terms. Oh, R is the correlation between x and y. Okay, and so if you find these 5 summary statistics here, then you just plug them in, you get your slope. Once you have your slope, you plug that into here. You have to find the slope first, and then you can get your intercept. And when we create these linear regression lines, so far I've just been calling them x and y, but a lot of times, we're always setting them up in the way to we want to make a prediction for the y variable based on the x variable. Okay, so when thinking about which one is x and which one is y, okay, we always use the x variable to make a prediction for the y variable. Okay, so we're using the x to make a prediction for the y variable. We have other names, okay, so some other names for the x and y variable. Okay, so the x variable and the y variable. Okay, so sometimes the x will be called the explanatory variable. Explanatory variable, and y would then be called the response variable. Okay. X is also called the predictor variable, and y might be called the predicted variable. And lastly, we may also call x the independent variable, and y would be the dependent variable. I don't really care for the terms independent and dependent variable. In my opinion, they suggest that there's a cause and effect relationship between x and y, as if y depends on the value of x, and that's not necessarily the case.
In this scenario, or always?
Just in general, okay? I mean, there might be a cause and effect relationship, but when you present your research findings to someone and you use terms like the the independent and dependent variable, people who aren't too familiar with statistics may then walk away thinking that there's a cause and effect relationship when there may not necessarily be one. There could be one, but not necessarily so. All right, so let's take a look at an example here. All right, and let's see what a regression equation can look like here. All right, so let's say our data set will be, books on a shelf. And for each book, we will count how many pages it has, count the number of pages, okay, and we will also measure its width. Okay, and so, so you can imagine, here's my picture of a book, stats, and we're going to look at the number of pages, and we're also going to measure the width of the book. Okay, so this is the width. And what we want to do is, based on the number of pages, we want to predict the width. Okay, so based on the pages, we want to predict the width of the book. And we'll say the width of the book will be measured in millimeters. Okay, width of the book. All right, so let's do our first clicker question. Okay, and so I'm going to just ask which variable is x. Okay, and so we will say A versus B. A will be a number of pages, and B will be width of the book. Okay, and if you if you want to talk to your neighbor about what you think is the x and what you think is the y, which variable is the x variable, you can turn to your neighbor and discuss. All right, I'm going to go ahead and close the poll. So if you haven't clicked, make sure you're clicking. Okay. All right. Okay, so almost everybody picked the correct answer, and I don't want to. If you pick the wrong one, that's okay. Okay, there's nothing wrong with picking the wrong one, but you're welcome to talk to your friends, or you talk to your neighbors in the class. Okay, and so if you didn't talk to anybody, next time talk to somebody. Okay, you don't have to be one of the three that got it wrong. All right, there's no reason, right? There's no reason for a situation like that. Okay. Sometimes you go the entire quarter sitting next to the same person, and then you never learn that person's name. So if you don't know the people sitting next to you, when class ends, you should turn and say, "Hey, what's your name?" Why don't we do that right now? Just turn to your neighbor and say, "Hey, I'm Miles," or whatever. Okay. All right. Let me get your attention back. All right. So I'm happy you guys are meeting each other, but we do have to we do have a few things to talk about. Okay, so we've determined which variable is x and which variable is y, because we are using x, the number of pages, to make a prediction for the width of the book. Okay, and so when we make our regression equation, it's y hat is equal to a plus b times x. And so what we can say, so this is you know, just based on the data, and the numbers have been calculated for us. Okay, values given to us actually in the textbook. So this example comes from the textbook. It says y hat is equal to 6.22 plus 0.0366 times x. Or we can say predicted width, or width hat, is equal to 6.22 plus 0.0366 times the number of pages. All right, so this is our regression equation. Or actually, I'll go ahead and I'll just copy all of this onto the next slide. So this is what our regression equation looks like. And so let's we'll do another clicker question, and we'll say if a book has 100 pages in it, you know, what do we predict for its width? What do we predict for its width? Okay, and so your answer choices will be 3.66, and let me do 6.586, and 9.88.
Is this in inches?
This is in millimeters. Millimeters, okay? So all of these in millimeters. And whoops, sorry. 2.276, and E will say 10.52. Okay. So go ahead and run this out. So talk to your newly met neighbors if you need to decide what the answer is. All right, I'm going to go ahead and close the poll. So if you haven't clicked, make sure you get your click in. Okay, and again, almost all of you got the correct answer. All right, and a couple of people got it wrong, but that's okay. All right, and so this, all we do is we just plug in. We have 100 pages, so I'm going to just have 0.0366 times pages. Pages is now the number 100. And so when I do this, I get 6.22 plus 3.66. I get 9.88. So my predicted width is equal to 9.88 millimeters. All right, so just quickly go ahead and we'll say if this is the different number of pages, our x, what do we predict its width to be? So we'll say predicted width. So at 100, we predicted it would be 9.88. If x is 200, what is the predicted width? And if x is 300, what is the predicted width? Go ahead and just take a minute to crunch out these numbers. Okay, no clicker question. Just write these down in your notes here. For 200 and 300 pages, what do we predict the width to be? Okay. Okay, did we get values here? Okay, for 200, what do we have? 13.54. Did you guys actually do this, or am I just pretending that you did? 17.2. Is this what we got? Okay, great. All right, how much did the predicted width change when we went from 100 to 200 pages? Okay, so how much did y hat change when x went from 100 to 200? What is that? Okay, so it increased by 3.66, all right? What about from 200 to 300? How much did it change? Also 3.66, right? If we did 17.2 minus 13.54, we get 3.66, all right? And so if I, disabled the multiplication button on your calculator and I said, what's your prediction for 400? What would you do? You would just add 3.66 and we would get, what, 20.86 if I did my multiplication there correctly. And where is this 3.66 coming from? Yeah, the 3.66, this is equal to my slope times 100. I'll put a dot, not to confuse you with x, okay? This is slope times 100. Slope is 0.0366 times 100, all right? And so this gives us some insight into the meaning of the slope. So if I can flip to the next slide here. What we had in our equation, we had y hat is equal to a plus b x, and we said y hat is equal to 6.22 plus 0.0366 times x. So my slope is equal to 0.0366. Excuse me. So what we have here is we are saying that if one book has 100 pages more than another book, we predict its width to be 3.66 millimeters more than the other. Okay? Or if we just wanted to reduce this just to a single page, okay? We can say, if we add one page, okay, or in other words, increase x by 1. If we add one page to the book, our prediction which is y hat, changes by 0.0366 millimeters, or the value of the slope. Okay, and so we can say the slope, kind of the interpretation of the slope. The interpretation of the slope is basically if x increases by 1, okay, our prediction for y changes by the amount of the slope. So, the slope, in our case, the slope is positive. And so this means, and it's a very small number, 0.0366, meaning if I add one page to a book, I expect it to increase just by the tiniest bit, right? And because that number is so small, it's not very useful to us. So we should probably talk about, increasing by 100 pages, and then we actually have a thickness that we can talk about. Okay, so that is the interpretation of the slope. We'll talk about the interpretation of the intercept on Friday, and some warnings about linear regression here. Okay, so we'll end here today, and we'll see you guys on Friday.